we are in La Chaux-de-Fonds, an industrial hub for Swiss watchmaking. This town, located in the canton of Neuchâtel, has been home to some of the most celebrated names in horology. Among them stands one with significant influence, Breitling. Today we are joined by the brand's chief operating officer, who will give us a transparent look around their facilities, showing how their watches are made. We'll see everything from R&D, design, assembly, and demonstrating the techniques perfected over its 140 plus years of history that have allowed Breitling to be one of Switzerland's most acclaimed watchmakers. Daniel, thank you so much for having us here at Breitling. So I know we have a lot in store at this site. So maybe if we can explain first, what are we going to see today and where exactly are we?
We are the manufacture chronometry, and in this specific building, we are focusing on the movement, development, and production until the homologation. And today I think we will start definitely from the beginning, where everything starts, meaning at the technical office, where we are doing the conception, the constructions of the movement. And then we will pass through all the different steps until the coming back to the homologations of the product.
So today is going to be a whole view of basically how a Breitling watch is constructed from an ideated concept to a finished product.
Absolutely.
Let's go.
Let's go. So here in this specific workshop, we are in the technical office, mostly for development of movement. And everything starts from here to do the first construction, conception, simulation, and then we can start with already a very good base for the prototyping.
So when you're developing something like this, like what is the thought process? Where does it start? How long does this take? Because I would imagine this is a lot of consideration. You used your B01, which that was 2009 consideration. I'm sure there was years of development before that. How did this process come about, and what are the ways that you're testing this?
But we have a certain number of constraints. First, as we were, of course, using our B01 movement, it was absolutely key to start on that. And today, as you know, there is few brands that have a perpetual calendar based on the chronograph movement. It was the first challenge. It's to be able to use our base to develop this specific module and then to have a very readable information on the dials.
And when you're manufacturing like a component like this whole perpetual module, is this something that you're doing and producing in-house? Like when you're designing this and then also developing it, like are you doing the prototyping right in this workshop as well and all that?
Some of the elements are done internally, especially for prototyping, but anyway, we are working closely with a certain number of partners specialized for every specific part. But again, what is for me the most important is the conceptions, because we are not talking only about the functions, we are really talking about at the same time the reliability of the movement. Of course, the price, the cost, it's also a very element, so we have to think a little bit how we will produce or we will assemble the movement, and even more important is then also the repairability, being able to do a service worldwide for our customer. And this is all the element we have to take into account in our own technical office. So today here we are in the laboratory who support the movement development as well the production. When we have, I would say, an issue or something, we can make all the tests and analysis. But most important is the support that it brings for the movement development. And here we can just see an example of what we do in terms of checking raw material to be sure of the quality of the raw material, or sometime on the surface treatment or on some element stand that we can observe on some component. Here we have the oscillating weight in 22 karat gold, on which we have seen some stand that we don't understand why it's here. And here, thanks to the analysis, we are able to provide the right action plan to correct the mistake.
So you have this table, the periodic table here, and it's going to give you an analysis based off of that scan.
Oh. Yes, and based on the result, we know if maybe just cleaning again the oscillating weight will solve the problem, or maybe we have to go back on during the process where we have identified something wrong.
I think the other thing I would stress here too is we're talking about deep magnification of this. Like this is almost beyond what like the naked eye is even going to notice, but this is the level of detail that you're looking at. You're still trying to You're chasing perfection as much as you can.
Absolutely, and here we see that because we are in the manufacturer, and of course manufacturer means that there is many things done by the human hands, but sometimes new technology help us to go behind these kind of things. Next step we want to see is the aging test. Here what we can see it's a test of the pusher, and we are doing aging who simulate 16 years.
So how long are these tests going to simulate 16 years?
So for this specific one, it takes 3 days, 24 hours, not stopping. If we have a failure, something happened, then we can do all the analysis to understand where come from the problem. Is it problem of dust, or is it the material, is it the assembly? And as we are in the process of ongoing improvement, when we bring a new material or a new supplier maybe, or we have changed something, we redo all the qualifications.
And then this is all linked up with like a data set, so you could probably figure out exactly when, at what point are you running into this aspect of wear and where things might break down both internally, but also could be more like externally, or when I say externally, maybe like something like the hands or anything of that could be thrown off.
At the same time, we are doing the simulation of the functions, so we have also analyzing how react the movement in terms of precision, stability, and things like that. Okay, now we are going to see a little bit the chronograph reset and observe what we can observe here. It's a simulation of what is doing the hands seconds when it's reset.
When you hit that reset pusher, this is basically slowed down. And what's the video of this? How many frames per second are we talking about here?
So here to have the ability to see something, it's 4,500 frames per second.
So if you ever reset a chronograph, you're going to see something here that might blow your mind if you've never seen it slow down to this degree.
Absolutely. The first time I have seen the image, I was also a little bit surprised, because when you observe with your own chronograph, it looks
like it settles right at 12 o'clock.
And here, this is the reality of what is doing the end seconds. It really goes a long way back, then coming again and again and again. And here you can see it seems it takes a long period of time before to stabilize. And this is, of course, done instantly. What it's important to see when we do that, it's to verify first that visually speaking, we can never see anything on the normal use of the watch. And the challenge here is to offer a very thin and delicate hands in terms of aesthetic and design, but at the same time very resistant, not only to one reset, but a reset done by a customer during at least 16 years.
What was like one of the considerations when you were doing these tests? Like, was there like a point where you were seeing a lot of like tension happening where something could actually break? Because when we look at chronograph hands, or just hands in general, we just think about the aesthetics, but in a chronograph, I mean, you are dealing with this reset. There's a lot of just torque that's being wound up, and you have to go back to this resting position. Was there a part of the component that actually was wearing down?
In fact, there is different parameters. The first one is, of course, the design itself, and for that, we need to play with the whiteness of the ends and the thickness, and also the selection of the material itself.
So you're trying to fortify that, but you don't want to get in the way of all the work that's been done on that design point of view too.
Absolutely. We try always to respect the designs that have been done in our studio design, to keep the code and everything, but at the same time, it must work. Okay, so today we have seen already different tests. We have seen simulation, we have talked about theory, but now we have the real life, and we have here exactly what a watch must resist. And here we simulate if we let the watch go down on the floor.
So shock test, basically.
Shock test. It's the worst one. And when we have done many other tests, at the end, this is the one which gives us the reality about the reliability of the product.
Should I do it?
Please.
All right. I love how we have all these complex machines, but then in a good old swinging hammer. What is this simulating? Like a drop test of a certain height?
Yes, normally it simulates 1 meter.
1 meter.
Yes, more or less you have your watch and it falls on the floor.
So if you had it like on your wrist or at a table, fall off, this would allow you to understand if that's going to withstand that.
And we do that for every new watches that we develop and bring to the market. Okay, Teddy, we are now in the micromechanics workshop. We have support for movement development, but also for watch and habillage development. At the same time, we have also production of some movement components.
So this is a feeder for a variety of different departments for Breitling.
Absolutely. Here we have our two CNC 5-axis on which we are doing cases, case back, bezel, crown, pusher, this kind of things. For example, here, just right there, we have example of other component we are doing, but this is to support the production. For example, we have the tray where we put the rubies, and then it will be used on the T0 workshop for the pick and play. But we need to have this kind of things, and here we are able to produce here also internally.
So these kits, even the kits, trays.
Exactly.
Okay.
So and this support the production that we will see in a minute.
Interesting.
Now we are going to the electro-erosion machine, where we can do very efficiently a lot of components. Here you can see the system. It works with a string that you can see here, on which we have 60 kilometers.
It's like a wire that will cut,
wires that cut the material. And here you can see some sample of different components that we are doing here. This is more for component for movement. If we have enough space, we put the same component but 2, 3, 4 times on the same plates. And with one step, we can then get many different components that we will usually use for the first phase of prototyping.
Why do you decide to still want to develop components in-house and do this?
Here in particular, it's to make the process of development more quick. It's time to market. Because if we are able, we do the simulation on the technical office, we do the prototype, then we test it directly just next door to the laboratory. We can see if there is some weaknesses or things to improve. Then we redo modification on the technical office, redo the prototyping here, retest and homologate. This is really a short and quick process development for any new component.
So Daniel, is there a specific component or like components that you're really thoughtful of wanting to maintain the know-how?
The balance wheel.
So you can actually still produce those here. Like you don't have to rely on suppliers if you don't need to.
For us, it's strategic to have this know-how, to conserve it, and we are still producing every day a certain number of our balance wheel that we are doing on this turning machine. And for example, with the example here, where we are starting from a bar on which
the raw material here.
We are doing all the turning. Of course, it's absolutely not the entire productions because we need much more than that. But it's important to keep and to conserve the know internally.
So what this will do is it'll go in this machine and it'll just gradually start cutting out the balance wheels.
But of course, we are using also this turning machine for other type of tiny component that we are able to do it. And again, it's very useful when we are doing prototyping for new movement or some improvement on some components that we first produce internally to do all the tests. Okay, now we are entering at the beginning of the production of the movements. So we are working on the milling workshops where we are doing all the components, all the evolution French. And here you have more or less the same type of equipment where we are doing at the same time the main plate, but also all the other bridges. There is 4 big steps. The first one is the milling itself of all the operation until we separate the component from the plate, which is done also in this workshop. And then we will move to do the sandblasting. This is an operation that we start to remove a little bit the
debris on the component.
Yes, and also all the mark of milling. And then we continue also with treatment of deburring with water high pressure jet.
So all of these machines here that we're looking at in this room can be programmed for specific components. They have a specific step and they'll get these plates on the inside like what we're seeing here, correct?
Here we have the right representation of all the 8 components we are producing here, they all start from the same shape.
It's like a raw material plate.
Yes, but even if the thickness is different depending of the need and the component.
So like a main plate will be a thicker material than like a bridge, for example.
Absolutely.
Yeah, okay.
And here, of course, we are always talking about the quality of the movement, quality of the component. But for us, what is also very important is to be able to produce efficiently. Efficiently meaning to master the quality and also master the efficiency. And you can see example of where we were producing at the beginning with only 2 or 3 components in the plate, and now we have optimized having 4.
And just to give a scale to this, I mean, if you have a main plate of a B01, there's going to be 350 plus components just on that movement. I mean, this is a small city that we're talking about on this scale.
Absolutely, here we are talking about 8 components out of more than 300.
Yeah. But even like for all the pivots for the main plate, I mean, you have to consider all these holes. Where,
Absolutely.
I mean, there's a lot going on for the programming of that.
No, this is definitely the most complex component.
All the pivot points, all the, I mean, it's...
And the precision must be really extreme, I will say. As soon as we have finished the process of the milling, it goes through sandblasting in order to remove all the marks of machining on the movement. And you will see a full automatized equipment where we can do both sides of the plate, where we will then remove completely the marks. At the same time, it's the first step to remove a little bit some bird that we still have after the machining. Next to this station, we will see another equipment where we will do by water high pressure on the plate to, at this stage, really remove completely the debris. And then we will just have a final handmade control. Here, as we are at the beginning of the production with the first element, the base of the movement that we are producing all years long, 24 hours per day, the quality of those components must be perfect. That's why we have had a few years ago new equipment that can do automatized control, both for dimension, also for the position of all the holes that we have. And thanks to this automatic new control equipment, we have been able to multiply by at least 10 the number of quality control we are doing during all the production process.
So what this can do is take after you've gone through the production of the milling, is we'll test before this goes to the watchmaker to do this assembly, and we're talking about
exactly.
T1, like they're able to have all this perfected to know that this is going to work once it gets in a human's hands.
It must be perfect to go to the next stage.
Yep.
That's it. But for that, it was really a difficult and long process of handmade control. And thanks with new technology, we have really improved again the reliability of the movement.
So Daniel, as we proceed through this concept of assembly, there's pre-assembly, there's something known as T0. So for somebody who's not familiar with that process, can you explain what happens in this room, what is done, and then also the scale of, you have human touch, and then you have automation that can happen depending on what needed to be done, correct?
Yes. Here we are in the pre-assembly, so meaning we are taking the different parts that have been produced again internally or purchased, and we put all together. Mm-hmm. Depending of the need, we can use, as you explained, manual press to assemble some tiny component. But when it's become more complex, and here we are talking about the garnissage, the word in French, where we put the rubies, the small pins on the main plate or on bridges. Here we are usually using more automatized equipment.
But there's still the level of human touch that will happen in this pre-assembly. So what are these technicians working on right here?
So here, for example, they are working on the different steps needed to assemble the mobile second chrono, which is certainly one of the most complex component in the movement, very long and precise axes. We have designed all the organization of the workshop around all the different steps needed to do it.
As we go to the next room, I think another thing to talk about here is a pre-assembly of maybe a broader movement, but then there's also individual parts that can be pre-assembled here as well. So we're talking about this central seconds, which is actually done in this department. So more complex movements you might have for a chronograph, you have this done at this stage, so that when you move to T1, the watchmaking process of assembly can move that much quicker.
Yes, because for example, here we are doing, knowing that in the chronograph we have more than 300 components. With the pre-assembly, where we take a certain number of components that we pull all together, or all the small elements like pin or stones that we put on the bridges or stone, at the end we have more or less 30 kits that we will go in the assembly line.
So you're basically here creating these kits, and what goes in those kits dependent on what the actual movement is and what the watch will be ultimately.
Absolutely, and of course we have, like we see here, manual operations depending of the needs, and then we can have more elaborate equipments and more automatized depending on what we want to reach.
So you have manual operation, you have semi-automated operation, you have like really full automation for depending on what the need is.
And we select the equipment depending of the complexity of the operation we have to do, depending also of the quantity we have to do. Some also the level of precision.
Because after this is going to go to T1, further assembly. If you don't get this right at this stage, you might create more work at the other next step.
In between the pre-assembly and the assembly, because we have to recheck everything and retouch many things. And everything we have in the past worked a lot to retouch. Now, with new equipment, we are both kind of equipment, we can have even better level of quality and repeatability.
In terms of setting these machines too, because it's automated doesn't mean that there's not steps required for manual intervention.
Absolutely.
How long does it take to actually set these machines?
When we perfectly master the equipment, anyway, it will take minimum 3 hours to set. But at the same time, if we go to the other automatized equipment, the time of setting will be even doubled. Here we arrive where we have one of the most complex automatized equipment that we use, for example, for the main plate, where we have the most number of components to be set, to be fixed on this main plate.
So all different components, and I can see there's like 35 different capacity for trays, and then it's smart enough to know to grab that component, put this part on the main plate.
Exactly what you have to go to take on the tray, to put perfectly with the right pressure, right precisions, and this is really key to master the quality.
Yeah, it's unbelievable.
So in this specific workshop, the réglage, we have 18 different steps. What is important is to just have a look on some of them. So over here you will see the operation where we assemble the collet inside the hairspring with a soldering operation, and this is what you can see here on the screen.
Applied a little bit of heat right to that point, and that's where it will become affixed to that central mass for the hairspring. And this is so crucial too, because you talk about this equilibrium as it goes to these other steps. That central mass and making sure that attachment point is perfect.
Yes,
it's so crucial.
It's a starting point where we start, and then we will go to all the other operation for the right balance of the balance wheel and the hairspring.
So this is just one of 18 steps that we're seeing.
Absolutely.
Here. Yeah. So another step over here that we're going to look at is ensuring that the balance will rotate properly. So we'll have that oscillation once a watchmaker will actually get it in his hand. So what we're seeing here is just this testing of once that hairspring is set, the balance wheel is in place, checking that rotation.
Absolutely, and this is really key, as if we miss this step, we will never be able to properly set the movement.
And what is a technician looking at as they're eyeing this? And they have this magnifier where they can see up close. What are they looking for with the balance's rotation, and how do they troubleshoot whether or not this is working properly?
One key element is the fact to have to double check that it's completely flat. It must not flip a little bit. It must be completely regular in terms of flatness. And this is one of the key elements to verify that then it will work properly.
So what we're seeing here is now with all the components, whether you're producing them, you're getting them from suppliers, testing them for ensuring that they're going to actually operate within your standard when you get into the watchmaker's hands feature, correct?
Absolutely. And so here we are on the incoming inspections for all components, and that's why as we are checking every 100% of the different components, we need also different type of equipment. First, good examples is this automatic barometer, meaning that on this specific equipment, we are checking all the barrel, meaning that we are checking if all the specifications are respected. And when everything fine, we know that the power reserve of the movement will be respected.
So this will be the barrel, and then also the mainspring is on the inside here, so you're able to actually... Okay.
And we can see also different because here we are passing through 100% of the production, huge volume, and here we have other kind of check. If, for example, we have the dimensional control of the oscillating weight of the B19, the specific versions that we have developed for the 140th anniversary, and here it's an example where one operator check individually all the different dimensional elements of the oscillating weight.
So they have this overlay where they can cross-check and make sure everything's in alignment.
Exactly, and this is a 2D measurement. And then when it's come for more complex component, and here, for example, we have the main plate. Here we have sent to a supplier for all the decoration and the treatment, surface treatment. And when it comes back, we redo all the dimensional control, but in 3D, to really verify there is no deformation or other defect.
And so 100% of these components, and just to kind of scale to this, I mean, you're talking hundreds and hundreds of components that have all their own protocol to be acceptable. So you have to develop the process for your own standard, and then you have to actually execute that internally.
Yes, absolutely. And we define for every component because the complexity it's not the same. And we have a specific protocol for every component. And we have a ratio between number of productions, the numbers that must be controlled. And if the level of quality is not reached, we reject all the lots.
So you'll have a statistical control group if it passes that number. So you've already done all this analysis so you can be efficient, and you've used statistics to be able to figure that out.
Exactly. So finally, we are at the assembly stage for the movement. And here we have very specific assembly automatic line. Everything starts here.
So you basically have a conveyor belt that will move all of these movements.
Here you have where we will put the vessel.
Yes, so it'll go in here, it'll go on this conveyor belt, and then you have all these stations. So these stations are developed based off of different steps of the assembly process, and then based off of that ID, it'll know what station for that movement it needs to stop at, correct?
Exactly, you can see here, it comes on the specific bench, and here, as an example, you have 10 vessels that will turn. Here at this station, it's 9 times because we have 9 specific operations.
And then the setup, if you look at a top-down view of this whole room, it's set up all around the process that is required to get these movements done. And then there's probably some like bottlenecks or steps that maybe take a little bit longer. So you have to think about methodically as someone who's overseeing the organization to this level and thinking about efficiency, like what are you looking at when you're setting up these stations? Like what are some of the other considerations on that front?
So at the end, what is important, it's how much time it takes for a certain of operations that we have designed for the bench. And here what you have seen at the first station, it was just one bench where we do this 9 operation. It's quite quick, and one station it's good enough. But for example, now we will arrive at the station where we are working on the chronograph mechanism. And here we have 14 different
steps for one station.
And all this operation takes quite a long time. And to equilibrate a little bit the production flow, we have here 3 bench doing the same operation. And so with the quicker one and the longer one, we equilibrate to don't lose time and really optimize the timing for the complete process. Of course, at the end, when we are talking, we will pass through, you see here the chronometry, where at the end of the process of assembly, we do all the performance tests, precision in 5 positions and so on. And then if we have to retouch or do some adjustment, then the movement pass through the hand of watchmaker, experienced watchmaker.
So this room is more for assembly of specialized movements. So we're looking here at B19. So we saw some of the assembly happening for some of the base caliber, so something like a B01, but there are additional steps that come with something like this that's being brought forward.
Yes, absolutely. And even as the B19 is done based on the B01, on the B01 base movement, we have some specific component. For example, we have the oscillating weight, inertial balance wheel. We have also a specific barrel, and this is prepared on the automatic line, and then it comes here to add the perpetual calendar modules.
And even the free sprung balance too. I mean, that's a different consideration for this movement. So this is going to be smaller capacity, so you're not going to be doing all your movements through here. So this is like special editions, maybe higher complications. That's what's usually going to take place
all
here.
the specialty that required high level of watchmaking know-how. When you consider that the timing to assemble a B19 versus a B01 could be 3 or 4 times
more. Really? Wow, okay.
Because there is, we have to consider that we have 2 high complications. For the chronograph movement itself, it's already a high complication on which we add a second module of high complication, which is a perpetual calendar.
Okay, so this is a room of technicians that might be a little bit more trained as like watchmakers here. So
absolutely, less operators, more watchmaker, and I will say even experienced watchmaker.
Okay, so this is where you get that higher touch type of aspect of Breitling.
And we have all the training for people to
build up to
increase
this step. Yes,
absolutely.
Okay.
Okay, so Teddy, now we're arriving finally at the end of the process. Here we are in the T2 workshop, meaning the casing, where the movement goes into the case and become waterproof.
So this is basically finishing up that watch head. So you have the movement, add the hand, the dial, get the case.
Absolutely. Here you can see we develop for any new development perfect setting, in particular for the very delicate operation, which is the ends setting.
So you'll stamp that down so you have all
and
those tools there.
And then we keep it ready to use for the new series. And then we start at the first step. This is where we put on the movement, the dials and the ends. This operation is done under laminar flow in order to avoid any dust, which is really painful for the movement and the watch.
Sure.
We continue to do with the casing, where we put the movement with the dials and the ends inside the case. We close it, and then from that we start all the controls for water resistance here. Then we have all the control for precision, power reserve. If something wrong happened aesthetically or technically, it goes back to those watchmakers. They can do what we call in French the décotage, to correct the mistake, redo again, and it repass through all the check again.
So Daniel, it's been a long day. I put you through the paces, but thank you so much for opening the doors to Breitling. Coming here, I've done a lot of manufacturer visits, but I can recognize the transparency of showing every single process, and I greatly appreciate it. I know people at home that want to understand more about Breitling appreciate it, so thanks again for doing this.
All right, thanks for coming, for help us to present our work, and we feel your passion about the watchmaking industry, so thank you for that.
Thank you, Daniel.
Thank you very much.